Right then, so the work problems for chapter 13 from Brown and LeMay. I want to give the credits first of all. So Brown and LeMay's chemistry, Zumdahl's chemistry, that's where a lot of these came from. Occasionally there will be a problem from McMurray and Fay's chemistry. That was the book I was using when I first started teaching many moons ago. And then also I've taken a lot of the multiple choice questions from Mr. Max AP Chemistry website, which you can find by going to Google or whatever and typing in Mr. Max, M-A-C, Max AP Chemistry website. So also the problems were arranged and also the solutions are provided by myself. Let's go to the next slide. And the next, and the next. All right, so here we go. Starting with this question where we're mixing pure methanol with water. They're both polar and the resulting solution feels warm. And let me get my marker working here. So remember that methanol is polar and water is polar because of those O's that are on them, because the O's are more electronegative than, for example, the H in water or the C and the H's in methanol. So the O's pull the electrons to themselves, which means they're partially negative. The H's and the C's are partially positive. So they're both polar. So when you do this, when you mix them together, it actually turns out, as we talked about in the lecture notes, that let's draw like a graph, and I'm not going to worry too much about the x-axis, but the y-axis I'm going to either make as entropy or not entropy, energy or enthalpy. So we can, and I'm saying this for a reason, because you're going to see this off and on through this semester, where you'll either see E over there or you'll see H. And these are kind of like almost like the same in some ways in that they behave the same way. They're not the same because the H, as we're going to see later, includes the work term. We'll talk about this when we talk about thermodynamics. So energy is just the energy, and enthalpy would be the energy, including not only the heat, but also the work. So the difference is that H would be the E plus the work term. But they both behave in kind of the same way. So really, typically you could see either of those on the left-hand side. So for this particular example, let's just get rid of the H and just call this E. So the energy of the separated water and methanol, let's put right there. And what happens, and let's say we do the reaction, and what's going to happen is that they're going to mix. There's going to be an activation energy, and then they're going to mix, and they're going to end up at an energy level, let's say right here. So the resulting energy of the solution will be lower. So it's more stable, and you'll want to remember that. It's the same thing to say something is more stable as to say that it's lower in energy. And the reason that it's lower in energy is because the solution has more entropy than the separated components. In other words, there's more randomness or disorder in the solution than there is when you have separated methanol and water. And there's also probably something in the delta H to do with this also, where the delta H will also be negative because when you mix these together energetically, it's more favorable for them to mix together. So when you mix them together, you have to separate the methanols, as we said in the lecture notes, and you have to separate the waters, and both those things are going to require energy. But then when you mix them, they're going to be so much more stable mixed together that they're actually going to give off energy. So there's going to be energy given off here as we go from the components or the reactant. They're not really reactants, but the components of the solution, as they go from components to the solution, they're going to give off this amount of energy here. And the way that that's given off in this case would be heat. And we're going to see other examples of things giving off energy in other forms like light later on in the semester. Next slide. So the answer here, which is kind of long, but if you want to just read it, I'll let you pause this if you want and read it on your own. But basically what we're saying here is that because these two things that we're mixing are both polar, then the solution is going to be more stable. Or in other words, the solution of the water and the methanol mixed together will be lower in energy than the separated components. So the energy drops, and the energy that was there before has to be given off in some kind of a form, which in this case is heat. So that's why it feels warm. Next slide. Okay, this particular problem is telling you that you have 25 milliliters of pentane and they give the density here. So let's stop for a moment. If the density of pentane is 0.63 grams per centimeter and you have 25, I'm sorry, it's centimeters to the third, and if you have 25 centimeters to the third of it, then if you multiply, let's see, yeah, if you multiply the 25 milliliters times the 0.63 grams per milliliter, you're going to find the mass in grams of the pentane. And then you can do the same thing down here for the hexane. So multiply 45 milliliters times 0.66 grams per milliliter, and you'll get the number of grams of hexane. And that's what you're going to need. You're not going to need the 25 milliliters. You may need those, but to start off with, what we're going to do for the first two at least is we're going to figure out how many moles we have of pentane and how many moles we have of hexane. So to do that, you're going to need the grams. Okay, so what I just said, let me just comment on that for one moment. A milliliter and a centimeter to the third and a cc are all the same thing. A cc stands for cubic centimeter, or in other words, a centimeter to the third, but it's easier and faster to say cc than it is to say centimeter to the third power. So, like mostly in hospitals, doctors, nurses will say cc's. And those are both equivalent to milliliters. All right, so what we're going to do, and I'm not going to actually do all of this with you. I'm going to let you do this as an exercise. I'll get you started, though. So let's look at these last two here at the bottom, the molality and the molarity. Let's go with the molarity first of the pentane. So we're only doing this for the pentane. So what you would do is find how many grams you have of the pentane, as I just said, and then you want to divide that by the molar mass of pentane to get the number of moles of pentane. And you'll need to do that for both the molarity and the molality. So you're going to be dividing by 5. Let's just draw a line across pentane's formula. It's C5H12. So the mass is 5 times 12 plus 12 times 1, which is going to be 72. So you, in other words, divide 25 grams. No, sorry, that's wrong. You would divide how many grams you've worked out when you did this multiplication before, where you multiplied the 25 times the 0.63. So it's going to be about, I would say about 16 grams, just guessing. And you'll divide that by your 72, which is the molar mass. So you divide how much you have by how much 1 mole weighs. So it would be about 16 divided by 72, and that would give you the number of moles you have. That will be necessary to do actually this one, and this one. So those three, for all of those, you're going to need the number of moles. And then what you'll do for the molarity is you'll just divide by the number of liters that you have of solvent. The solution. So the solution will be how much you have total, which means you'll have to add the 25 milliliters of the solute, which is pentane, to the 45 milliliters of the hexane. So 25 milliliters of the solute plus 45 milliliters of the solvent will give you 70 milliliters of solution. So you want to figure out, first of all, how many moles you have of the pentane and divide it by liters of solution for the molarity. So the easiest way to do that is figure out how many moles you have of the pentane, and then divide that by, in this case, it would be 0.07 liters. Because when you add 25 and 45, you get 70 milliliters, which is 0.07 liters. So divide the number of moles, which I'll leave that blank on top, and then divide by 0.07 liters. And that will give you your molarity. To do the molality, you have to do it slightly differently. So you start off the same way, so 0.07 liters. So that's for the M. That's for the capital M. Okay, for the molality, you start off the same way, so you can use the same number you got from the molarity, the number of moles of pentane. But for the molality, M-O-L-A-L-I-T-Y, you want to divide by kilograms of the solvent. So what you'll have to do is you'll have to figure out, and maybe you've already done this, but you want to multiply 45 times 0.66, which is going to be about 30 grams of hexane that you would have, and that's just multiplying the density times the volume to get the mass. So let's just say it's 30 grams of hexane. Well, that's the solvent. So let me come over here to the left. So for the molality, the lowercase m, you want the moles of solute, which you've already figured out in the other part. So whatever that was, put that on top, and then you divide that by the number of kilograms of the solvent. So if you multiply 0.66 times 45, you're going to get 30, I think. So that would be 30 what grams, but we don't want grams, we want kilograms, so we have to divide that by 1,000, so that would be 0.03 kilograms. So that would be the difference between the molarity and the molality. So 0.03 kilograms for this one. And then to do the mole fraction, you just find how many moles you have of the hexane and how many moles you have of the pentane and add them together to get the total number of moles, and then take the number of moles that you had already found for pentane and divide it by the total number of moles, and that's going to give you some decimal, like I don't know, 0.5 or whatever. So that's going to be your mole fraction. And then the mass percent, you don't have to use the moles. You just take the number of grams you got initially here for pentane by multiplying 25 times 0.63, and then you want to divide that by the total mass, which would be that mass plus what you got when you multiply 45 times 0.66. And then you multiply that by 100%. So that's how you get the mass percent. So I'm going to stop here and let you guys go ahead and do that on your own, and I'm going to move on, and the answers are on the next slide here, and I'm going to go ahead and let you pause here and look at this and see if you got the answers right, and then I'm going to move on to the next problem, which is the solubility of nitrogen in water is 8.21 times 10 to the minus 4th molar at 0 degrees when the N2 pressure is 0.79 atmospheres. Find the Henry's law constant for this in the form of that equation right there. And then we're also supposed to do the solubility a second time when the temperature, when the pressure has been raised from 0.79 to 1.1. To do the first part, let's just put A here. We'll use C equals Kp, but we're trying to find K. So I'm going to rewrite C equals Kp, which is written up here. I'm going to rearrange it to get K by itself, and that's going to be C over P, where C is the concentration, which is another way of saying molarity, moles per liter. So it's going to be that over P. We want the P to be in atmospheres. We want the concentration to be in moles per liter. So here's your concentration in moles per liter, and here's your pressure. So we divide the 8.21 E minus 4 by 0.79 to get the K, and that is the answer to part 1. We just are supposed to find what K is. So when you're doing these kinds of problems, be sure your units line up correctly. To do the second part, we then go back to the original equation here, and now we know what K is, but we don't know what C is now because we've changed the pressure. So just take the K that you figured out here in part A and multiply it now by 1.1 atmospheres, and that will give you either the concentration or the molarity, or now they're introducing a third term, solubility. So notice all of these three things are synonymous: solubility, molarity, and concentration. Anyway, that's going to give you the answer to part B. Just multiply the K that you figured out in part A times 1.1 atmosphere, and that will give you the answer to part B. Next slide. So here are the answers. If you want, you can pause here and look at the actual numbers. There's a whole lot of work problems in this chapter, so I'm going to go ahead and keep going. So let's go to the next one. Glycerin is a non-volatile liquid. That means it doesn't evaporate. If you put it in water, then as we said in the lecture notes, the water's vapor pressure is going to go down. So we're going to need to know what the vapor pressure water is at 39.8 or about 40 degrees centigrade. Remember we said that at room temperature, 25 degrees centigrade, the vapor pressure water is about 24. So notice how much it's gone up. We raised the temperature from 25 to about 40, and the vapor pressure goes up by more than a factor of 2. And that's the way it is for water. The more you heat it up, the vapor pressure goes up a lot. So anyway, so we know what the vapor pressure of pure water is. So remember our formula here is going to be, and for this particular problem, they're giving us a density at this temperature. And this, I think this is either the only time this is going to happen all semester, or maybe one of only 2 times. So just for this one particular example, we have to take the amount of water, which was 338 milliliters, and multiply by the density. And let's see, yeah, that would be right. So to get the number of grams, it's not going to be 338. Now, ordinarily, in any other problem except basically this one, we would just assume that 338 milliliters of water weighs 338 grams. In this case, though, we won't do that because they're actually telling us what the density is, but it's going to turn out not to really matter that much. And on a multiple choice question, you could probably just forget about that and just assume that it's 1, and you'd still probably get the right answer. But let's just do it the way that they want us to do it. So I think that when you multiply 338 times 0.992, you get something like either 337 or 336. So, I mean, let's just take a chance and say 336. So that's how many grams you would have. All right, so Raoult's law says that the vapor pressure of a solution, which I'll actually take a few moments and write this out, although we don't really have time, but let's just say that the vapor pressure of the solution, I'm just going to use S, I'd usually write SOL, equals the mole fraction of the thing that's, whatever it is that's volatile, times the pressure of the pure liquid like water. So in this case, the pressure of the pure water would be 54.74 torr here. And the mole fraction of the water would be the amount of moles of water. And to get that, you divide how many grams of water you have, which I'm saying is about 336, divided by its molar mass, which is 18. So how much you have, which is 336, divided by how much 1 mole weighs. So 18 grams per mole. So divide 336 by 18, that'll give you the moles of water. And then whatever you, so it's going to be about 5 times 3 is 15, 16, 17, 18 maybe, something like that. And then you also have to add how many moles you have of the glycerin. So you'll have to figure out what the molar mass is of glycerin by multiplying 3 times 12 plus 8 times 1 plus 3 times 16. And then divide how much you have, which is 164 grams, by how much 1 mole weighs, which is whatever you got when you did all of that, which I could do it in my head, but I'm not going to because of time. So anyway, once you figure out how many moles you have of glycerin, you add that to the number of moles you have of the water. And then to get the mole fraction of water, you divide how many moles of water you have by how many moles you have total. Then that goes here. And then the pressure of the water when it's pure is 54.74, so that goes here. So all you have to do then is multiply these two things here together, and that will give you your answer, which I'm going to go to the answer now next. And here is what we actually got for the number of moles of water. The number of moles of glycerin turns out to be 164 divided by 92, so 92 is what we would have gotten if we added all of these things here together. And that was 1.783 moles. The water was about 18.6 moles. So add these two numbers together to get the total number of moles, and then divide the number of moles of water by the total number of moles, which is done here. So divide 18.6 by 20.4, and you get 0.91. And that's the mole fraction of the water, which is the thing that we care about. Multiply that then times the pure water's vapor pressure, which is 54.74, and that will give you the vapor pressure of the solution. So the answer is about 50 torr here. Next. Okay, so Raoult's law says that the pressure of the solution equals the mole fraction of the volatile component times its pure vapor pressure. So let's write this as chi times the pure vapor pressure, which I'm just going to write as P naught. And in this case, we actually don't have water, we have diethyl ether, but it works the same way. All right, and then it tells us in this first statement that the normal boiling point for diethyl ether is 34.5 degrees centigrade, which we would want to convert that to Kelvin by adding it to 273. And then, but you don't actually have to even do that for this problem, so you don't actually have to do that because we don't need it. A solution containing a non-volatile solute is dissolved in diethyl ether, and it has a vapor pressure of 698 torr at this same temperature. So again, don't convert that to Kelvin because it's not necessary. But notice that it doesn't change. So here's our formula. So what we're asked to do is find the mole fraction. So you can rearrange this, which I'm not going to take the time to write it out, but it would be the P of the solution divided by the P naught. In other words, the vapor pressure of the solution divided by the pure vapor pressure, which we are not given, but we're given the pressure of the solution here. So you have to read this carefully. The solution has a vapor pressure of 698, so that goes here. So your formula, I mean, it's just so long to write things out. So the formula is going to be that chi equals PS over P naught, and the PS is going to be 698 torr. But what's the P naught? And they don't really give you any way to figure this out. So you either can't do the problem at all, or you have to realize that when they say the normal boiling point, what they mean is the boiling point at 1 atmosphere. So at 1 atmosphere of pressure, that means that in order to overcome 1 atmosphere pressure and boil, then this thing has to have a vapor pressure of 1 atmosphere. So in other words, what they're saying is that at 1 atmosphere, the pure vapor pressure here for diethyl ether would be 1 atmosphere at this particular temperature. So if you divide 698 by 1 atmosphere converted to torr, which is 760, so normal boiling point means 1 atmosphere. In other words, like in Houston, the normal boiling point would be 100 degrees for water, because we're at 1 atmosphere. That's supposed to be an A, TM, which equals 760 torr. So what we're saying here, or what they're saying, is that the pure boiling pressure here, the pressure of the pure liquid, the vapor pressure would be 760 at that temperature, because it boils at that temperature. So 760 torr. So if we divide PS by P naught, we're dividing 698 by 760. And that's going to give us chi here, which is the mole fraction, and that's what they're asking for. So in other words, to do this problem, if you get this on a test, all you have to do is divide 698 by 760, and you have your answer, which that's about 700 divided by 760, which, you know, I'm going to guess it's about 0.8 or 0.9 or something like that. Let's go to the next slide. So it's 0.918. So again, notice this is actually very easy if you understand what's going on. You just divide 698 by 760. So the key here is to remember that when they say normal boiling point, I have a note down at the bottom here. When they say normal boiling point, so you have to remember that word normal means that it's taken at 1 atmosphere, which I guess they're considering that to be the normal circumstances. Next slide. Okay, what mass of glycerin, and here we're given the formula so we can figure out the mass if we need to, which is a non-electrolyte, must be dissolved in 200 grams of water to give a solution with a freezing point of minus 1.5 degrees centigrade, where we're going to use this formula, delta T equals IMK, and I'm going to leave I out because I is 1, because C3H8O3 is a covalent compound. So it's just, I'm going to write MK where the I is actually 1. And we are not given K here. However, let's see. Yeah, so we'd have to have that, but it would have been given in the problem statement. In this case, I think it's going to have been given in a chart above the set of problems that I actually took this from. All right, so what we have here is we have delta T. Delta T is 1.5 degrees centigrade, not minus. Because remember, when we do the freezing points, we just automatically subtract. So delta T is actually 1.5 degrees centigrade. And we need to know what mass we have to dissolve in 200 grams of water. All right, so we'll actually look at the numbers and the K value on the next slide and the answer. But basically what we're going to want to do is we're going to divide the delta T here by whatever the K is. We're going to divide those, and that's going to give us M, or the molality. And then we can go ahead and write that out. So, for example, we can write that M, lowercase m, equals such and such a number of moles of the solute per kilogram of solvent, which in this case the solvent is the thing it's dissolved in, which is your water. And then what we can do is we can multiply that by 0.2 because we don't actually have 1 kilogram. So if we multiply that number by 0.2 kilograms, then the kilograms are going to cancel, and that's going to give us the number of moles of glycerin. And then it just remains to convert moles of glycerin to mass of glycerin by multiplying by the molar mass. So let's go ahead and go to the answer. So when we do what I said and we divide the delta T by the K, and the K was 1.86 degrees centigrade per, or times kilograms per mole, we get 0.806, and that's moles of solute per kilogram of solvent. So if we had 1,000 grams, we would have 0.806 moles, but we don't. So what we can do is we can multiply this by 0.2, and that will tell us how many moles we would have if we only had 200 grams of solvent, or in other words, 200 grams of water. And then we can convert that number of moles, whatever it is, to grams by multiplying by whatever you get when you multiply 3 times 12 plus 8 times 0, 8 times 1 plus 3 times 16. Right, so the way that I did it here is actually the same thing, but I just did it in the reverse order. So first of all, I took it in moles per kilogram and I multiplied it by, let's see, I actually converted that to grams first by multiplying 0.806 moles of glycerin times 92 grams per mole. So when you add 3 times 12 plus 8 times 1 plus 3 times 16, you get 92. And so I went ahead and converted it first of all to 74.2 grams and then multiplied that by 0.2, which gave me the same answer I would have gotten if I did it the other way, which is 14.8 grams. All right, so just looking back over this, we want to use this formula. We realize I is 1 here, so we can just get rid of it. So we have to first of all find the molality, and we get that by dividing delta T by K. Once we get that, we just write out what is that. Well, molality is moles of solute per kilogram of solvent. And then we realize if we want to know how much we have in 200 grams of solvent, it would only be 1/5 that much, right? So we can find how many moles we would have in 200 grams by multiplying that number right there by 0.2. And then that will give us how many moles we have in 200 grams of water. And then to convert it to grams, and the reason we're doing that is because they're asking for the mass, then we just multiply by the molar mass, which is 92 grams per mole. Here, let me re-underline it right there. Okay, next slide. Find the freezing and boiling point for each of these. We're only going to do it for one, and it's 5 grams of NaCl and 25 grams of water. So the formula is going to be the same for both of these. Let's very quickly write. It's delta T for both of them is going to be IMK. It just takes so long to write with this thing. Equals IMK. What's I going to be? So while I'm taking 15 minutes to write this out, why don't you just think about what I will be for NaCl? Okay, so there we go. So it will be, you should have come up with 2, right? So I should be 2 for NaCl. NaCl is a soluble salt, so if you put it in water, it breaks up in Na plus and Cl minus. So that's a total of 2 particles. So the I will be 2. And actually, let's see, we're supposed to find delta T, so we need to know what M is. So let's come back to that, and let's go ahead and look at K. So K in water, K is going to be one value for K freezing and one value that's different for K boiling. So we'll have to go to the next slide and get those. So we're going to do 2 parts to this, one for freezing and one for boiling. So, but before we go to the next slide, let's figure out what the molality is. So the molality is moles, or in this case it's formula units, but it's moles of solute per kilogram of solvent. So here we would have to, we have to convert that. It's easier just to do it this way. Just convert that to kilograms. So 25 grams would be 0.025 kilograms, where all I did was I moved, or you could say multiplied by 1,000, or moved the decimal place back 3 places to the left, which is the same thing. But now you've got kilograms instead of grams, and that's what we want to divide by to get the molality. And then what do we want to divide by that? We want to divide the number of moles of solute. The solute's NaCl. So to get the number of moles of NaCl, we would divide 5, which is how much we have, by how much one formula unit is, which is, I believe, 23 for sodium and 35.5 for chlorine. So that would be 35, 45, 55, 58.5. So you would divide 5 by 58.5, and that will tell you the number of moles of solute you have. Okay, so divide 5 by 58.5. If you want to do it, if you have a calculator, do it now, see what you get. That's going to be the number of moles of NaCl. And then you're going to want to divide that by your volume, and your mass of kilograms of your solute, which is 0.025 kilograms. And that's going to give you your lowercase m, or your molality. So whatever you get when you divide 5 by 58.5 is going to go right here on top, and you divide that by 0.025 kilograms, and that'll give you your molality. Or you can do this as a ratio and proportion if you want to, if it's easier for you to see that. I actually did it that way for years because it was easier for me to see what was going on. And then I got to the point where I was familiar enough with it that I could just do it the shortcut way, which is the way I just showed you. So just find the number of moles and divide by how many kilograms you have of the water. And then that will give you your M, this thing right here. And then to get the answer for the boiling point, for example, you would multiply 2 times whatever you get when you do this, and then times whatever Kb is. And then to do it for the freezing point, you do the same thing, but instead of multiplying by Kb, you do it times Kf. So let's go to the next slide. So when we divide the number of moles here, which turned out to be 0.0855, by 0.025, we get that the molality is 3.419 moles per kilogram of water. So we're going to put this number into both of our answers here. We're going to put it here for the freezing point, and then we're going to put it here for the boiling point. Now, where is it? There. So that's the molality. The 2's in both of these, here and also down here, are the I numbers, the number of particles that NaCl breaks up into. And then for the freezing point, you use 1.86 degrees centigrade, blah, blah, blah. And then for the boiling point, you use 0.51 degrees centigrade kilogram per mole. And then just multiply these out. So when you multiply these out, for the freezing point, you get delta T is 13, and for the boiling point, you get that delta T is 3.49 degrees centigrade. And then remember, that's just the delta T, but they're asking for the freezing point and the boiling point. So you then, for the freezing point, you have to remember that I've got to subtract that from 0. So 0 minus 13 would be minus 13 degrees centigrade, and for the boiling point, you add it to 100. So it would be 103.5 degrees centigrade. Next slide. All right, here we have a Raoult's law thing, which is a little complicated. So we start off by mixing 50 grams of acetone. That's not what we need. We need the number of moles. And 50 grams of methanol. So we're going to have to find the molar masses of these. So you're going to have to add 16 plus 3 times 12 plus 6 times 1. For this one, same thing here. So that's going to be 12 and 16, 28, 32. So this one, I can just tell you is going to be 32 just by looking at it. Do the same thing for your acetone over here to get it so that you know how many grams are in 1 mole. And then we need to find the number of moles of each of these, and we'll get to the questions in a moment. So whatever you get here, you're going to divide for acetone 50 grams, which is how much you have, by how much 1 mole weighs, which is what you would get if you add these values together to get the molar mass. And then do the same thing for the methanol. So you have 50 grams and 1 mole weighs 32 grams per mole. So you divide 50 by 32 for the methanol. And that will give you the number of moles of methanol, and then you add them together. Now these are both volatile, so we're going to have to use, and it just takes too long, and there are too many slides in this thing, and we're already after a half an hour. So I'm just going to stop writing for the most part, but the formula is going to be that the pressure of the solution will be Chi times the pure vapor pressure of A plus Chi B times the pure vapor pressure of B, where let's just let acetone be A and methanol be B. So we're going to have to first of all do what I said and find the number of moles of acetone, find the number of moles of methanol, and then add them together to get the total number of moles. And then the number of moles of acetone divided by the total will be the mole fraction of acetone. The mole number of methanol divided by the total number of moles will be the mole fraction for methanol. So those are going to be the Chi-A and the Chi-B. Then we want to multiply by the pure vapor pressure, which for acetone at this particular temperature is 271 torr, and for the methanol is 143 torr. And I don't know if we can go any further really without going to the answer. So let's just move on to the next slide. So to do what I said, we have 50 grams of acetone. Turns out the molar mass is 58 when you add all of these things here together. So you divide how much you have, which is 50 grams, by how much 1 mole weighs, which is 58 grams, and you get 0.862 moles of acetone. Do the same thing for your methanol. How much you have divided by how much 1 mole weighs, and you get about 1.5 moles of methanol. Total would be 1.56 moles plus 0.862 moles here, which would be 2.42. So if I divide this number here by 2.4245, I get the mole fraction for the acetone, and if I divide that number by 2.4245, which is the total, I get the mole fraction for the methanol. So that, in other words, I get the Chi-A when I do the first thing and the Chi-B when I do the second thing. These two things here, the pure vapor pressure for A and B, were given in the problem statement here and here. So here's A and here's B. So the answer is going to be put these two numbers in for the pure vapor pressures and multiply. So this number comes here. This number here comes down here. Now notice here that when you add 0.6444 to 0.3555, you get 1. And that's what it should do because you've only got two components. So two components means that if you have two mole fractions, they should add to be 1. So when you do this calculation here, you get that the vapor pressure of the solution is about 188.5 torr. And you don't have to convert this to atmospheres. We can just leave it as torr. Okay, so this other part is asking us what is the composition of the vapor expressed as a mole fraction. So in other words, what we figured out here at the top was the composition of the liquid as a mole fraction. We said the liquid's mole fraction for acetone was 0.355, which I'm overlining, and for the methanol it was 0.644. But again, that was for the liquid. But now you aren't going to probably ever see this again, maybe in your life, but they just want to do this little exercise, so we won't spend a lot of time on it. But if you wanted to do this part where it says what is the composition of the vapor as a mole fraction, you would multiply these two numbers together, and that's going to give you a certain value, which is 96.34, which I've written here, and divide it by the total pressure, the total vapor pressure of 188.5 torr here, which is done here, and you get it's about 0.5. And then do the same thing here, multiply these two numbers together, and then divide whatever you get by the total pressure, which is 188, and that's done here. And when you do that, you get a little bit less than 0.5. Now, I might just remark here that it's odd because we started off with, let's see, the mole fraction of the acetone was only about 1/3 roughly, and the mole fraction of the methanol was about 2/3. So in the liquid, you had about 1/3 acetone, about 2/3 methanol. So you might expect that in the vapor it would be the same, and it isn't, because you can come down here and see they're both about 1/2. And the reason is because even though there's less of the acetone here, it's much more volatile. In fact, it's twice as volatile because its pressure is 271 and the pressure of the methanol is only 1/2 that much roughly. So when you take that into account, it turns out that they're present in roughly the same amount in the vapor phase. And then they say the last part of this long problem is they say the actual pressure is 161. What did we expect it to be? We expected it to be 188. So calculating it theoretically or a priori, we got 188. It's only 161 in practice, and the reason is because this is one of those scenarios where we have a negative deviation like we talked about in the lecture notes. Because acetone and methanol are both polar, they hold each other down in the solution. So not as much evaporates as we would have expected. And it turns out that it's considerably less than 188. Okay, so having said that, we're finished with this. Let's move on. Okay, a solution is made by dissolving 25.8 grams of urea, a non-electrolyte, in 275 grams of water. Find the vapor pressures at 25 and 45. And then they give us the pure water vapor pressures at those two temperatures. So we're going to use a simple form of Raoult's law, which is going to be the pressure of the solution, which is what we're trying to find at two different temperatures. But it's just the same problem done twice. Is going to be the mole fraction, which we'll figure out once and use it in both parts. And that's going to be multiplied by the pure vapor pressure. So the really harder part of this is finding the mole fraction. So we have to figure out what the molar mass of that is, and then whatever that is, we'll divide 25.8 grams of it, which is how much we have, by how much 1 mole weighs, and that gives us the number of moles of the urea. And then we have to figure out how many moles we have of water. In this case, we have 275 grams of water, so we divide that by 18, and that will tell us the number of moles of water, which we'll see that on the next slide. So we'll then add them together and get the total number of moles, and then divide the number of moles of water by the total number of moles to get the mole fraction of water, which is the thing we care about because that's the thing that's volatile. Once we have that, we'll have chi for the water, and then for part A, we'll multiply that by 23.8 torr, and that will give us the pressure of the solution in torr, and for part B, we'll multiply by 71.9. Next slide. So for part A, first of all, we figure out that we have 275 is how much we have grams of water divided by 18 grams per mole, which is how much 1 mole of water weighs. In other words, it's its molar mass. We get 15.3 roughly moles of water, and when we divide 25 by 60, which is the mass of the urea, we get 0.43 moles. So we add these together and get the total, which is about 15.7 moles, and we divide the number of moles of water here by the total number of moles here, and we get that the mole fraction of water is 0.9726, which we're then going to multiply in turn by the two different pressures at the two different temperatures, 23.8 and 71.9. For the first one, the lower one, we get 23.14, which we round to 23.2, and for the second one, we get 69.9, which we round to 70. Next slide. Okay, so there are a few multiple choices we'll go through now. These were taken from Mr. Mack's website, and I'm going to go through some of these a little more quickly because of the time factor. So this one is very easy. Pressure has an appreciable effect on the solubility of what in liquids? The answer here is going to be gases. And if you'll just remember back to what we said in the lecture notes, if you want to put more of a gas in a liquid, like for example Coca-Cola, then you can do it by increasing the pressure of the carbon dioxide gas above the liquid. So our answer is C here. Let's go to the next slide. And next, the concentration of a benzene solution prepared by mixing 12 grams of benzene with 38 grams of carbon tet is blank mole Lao. This is mole Lao, so it's the lowercase m. So we need the moles of solute over the kilograms of solvent. The solvent in this case is the carbon tet, which that's short for carbon tetrachloride. We have I'm not going to write it out, but we have 0.038 kilograms of that. And the number of moles of the C6H6 would be 12, which is how much we have, divided by the molar mass. Whoops. Sorry about that. This thing kind of goes crazy sometimes. The molar mass of C6H6, which hopefully you can still read that, which would be 6 times 12 plus 6 times 1, which is 78. So you divide 78 by 12, and that will give you the number of moles of your solute, which in this case is benzene. Now, this is a little unusual because you're mixing basically two liquids here, but and one of them is benzene and one is carbon tetrachloride. But anyway, so you're going to take the number of moles, which is what you get when you divide 12 by 78, which is about 1.6. So it's going to be like about 0.17 or 0.18 moles. And then you divide that by 0.038 kilograms. And whatever you get when you do that is going to be your answer, which I can't do that in my head. So let's go to the next slide. So when we divide the 12 grams that we have of the benzene by the 78 grams per mole, we get 0.154 moles, which we divide now by 0.038 kilograms, and we get 4.05, which is not exactly the same as this answer choice, but it's probably the right one because none of the other ones are even close. Now again, down here at the bottom, if you want, you can do this as a ratio and proportion. It's up to you, and again, I did it that way for years, but it's easier just to do it this way, where you just find the number of moles and find the number of kilograms and then just divide. To do a ratio and proportion, and you can email me or whatever if you want, if you don't understand what I mean by that, but what you would do would be that you would say I've got 0.154 moles in this 38 kilograms, so that equals X over 100, or I'm sorry, over 0.038. I don't know. Let me start over because I think I said that wrong. 0.154 moles is to 0.038 kilograms, as X number of moles would be to 1 kilogram, and cross multiply. And you wind up with the same thing you wind up with here, but it's just, I don't know, just maybe it was just me. It was just easier for me to see it that way. But this is the shorter way to do it. Anyway, let's go on. All right, so we want molarity in this one, so we're going to need the number of moles of solute to start with. The solute here is HCl. We have 5.5 grams of it. We need to convert that to moles, so we divide by the mass of HCl, which is 1 for H and 35.5 for Cl, which is 36.5 total. So we divide 5.5, which is how much we have, by 36.5, which is the molar mass, which is how much 1 mole weighs. And that will give us the number of moles of the HCl, which is the solute. And then we also are going to need to know the number of liters we have of the solution, which would be both the solute and the solvent. And we have to do this one a little oddly because they give it to us in a different way. So they're telling us the density of the solution is 0.79 grams per milliliter, which I'm going to invert that and flip it upside down and say, instead of writing it as 0.79 grams over 1 milliliter, I'm going to flip it upside down and write it as 1 milliliter over 0.79 grams. And then I'm going to multiply that times 205.5 grams, which is the total mass of everything in the solution. So whatever I get when I multiply those is going to be the mass, it's going to be the number of milliliters of the volume of the whole solution. So if I get that, it's going to be in milliliters, and then what I'm going to want to do is convert that to liters, which means I'm going to have to move the decimal place back 3 places to the left, and that will convert it to liters. And then I'll take the original number of moles of HCl that I got and divide it by the number of liters that I got, and that's going to give me my answer. So let's go ahead and look at that next. All right, so when we do the 5.5 divided by the 36.5, and that 36.5 there is what you get when you add 35.5 for chlorine from the chart to 1 for hydrogen, right? You get 0.1507 moles of that, and that's the solute. Now we need to know how much volume we have of the solution. So flip that conversion factor upside down, and you can do that because they're both just multiplying by 1. And if you don't understand that, I'll probably mention it at some point, or you can just email and ask me what I mean by that. But I just turned this upside down and multiplied it by the total mass of the solution, where you have to add these two things together because you have both in the solution. So you have to add the total mass. So that would be 205.5 multiplied by our conversion factor here, and we get 260 milliliters, which is going to be the same thing as 0.26013 liters. So divide the moles by the liters, and you get the molarity. And I got 0.58, and comparing with the answer choices, 0.58, 0.58, 0.58, here it is. So that is our answer choice E. Next. Which one of the following concentration varies with temperature? And we've already said this, it's molarity. And the reason is because the volume varies with temperature. Whereas for molality, for example, you're doing it moles of solute per kilogram of solvent, and that doesn't vary. The mass doesn't vary, but the volume can. So if you're doing something that involves a volume, it can vary with temperature. Like molarity, because it's moles of solute per liter, which is a volume of solution. So the answer is D. Next. The vapor pressure pure ethanol is 0.459. Ignore that slash. This is taken from, I'm going to blame Mr. Mack's website for that. Okay, so it's 0.459 atmospheres. So if you dissolve 10 millimoles of something that's not volatile and 90 moles of ethanol, which is volatile, we already discovered that, right? What's the mole fraction of the ethanol? Well, you can just look at this. I mean, it's going to be 0.9, right? Because you've got a total of 100 millimoles, of which 90 are ethanol. And we don't care about this because it's not volatile. So the mole fraction of the thing that we do care about, which is the volatile component, which is the ethanol, is going to be 0.9, which I'll just very quickly try to write that. You can see how hard it is to do this. I complain a lot. So the mole fraction for the ethanol is going to be 0.9, which I'm going to multiply by the vapor pressure, the pure vapor pressure of ethanol at this temperature, which is 0.459, which I can just look at it and round off. If I round off 0.459 to 0.45, just for the sake of doing this problem, I mean, I wouldn't do that. If I were actually doing this, I'd be using a piece of paper or a screen and a calculator, and I'd do it exactly. But I mean, just roughly, 0.9 times 0.45 is going to be about 0.4, which it turns out that there is an answer choice that's close, and that's answer choice B. Now, whether that's right or not, we'll find out now. Let's go to the next slide. And it actually turned out to be correct. So anyway, 90 divided by 100 is 0.9. And 0.9 times 0.459, which I got from right here, is 0.413 atmospheres, which is choice B here. So again, our formula is here. Let me just go over it again real quickly. So the pressure of the solution is the mole fraction of the solvent that you care about. Not, in this case, that would be the ethanol, not the naphthalene. So naphthalene is the stuff they put in mothballs, and it doesn't like evaporate like ethanol. It doesn't have a vapor pressure. We divide how many moles we have of the thing that we care about, of the thing that's volatile, divided by the total number of moles, and that gives us the mole fraction, which is 0.9. So because this was kind of an easy one, let me just take a second here and say that the mole fraction is always going to be a number between 0 and 1. So in this case, it's correct because it's a number between 0 and 1. All right, let's go to the next slide. The vapor pressure of pure water at 25 degrees is about 24 torr. So determine the vapor pressure above a solution prepared by dissolving 35 grams of urea in 75 grams of water. Okay, I'm just going to get you started on this one because we still have some other problems to do that are actually kind of difficult. So I'm going to try to save some time for those. So let me just set this one up. It's going to be done the same way as the ones we just did. You want to find the mole fraction of the water. So you're going to have a solution that has water in it, which we care about because it's volatile, and urea in it also, which we don't care about because it's not volatile. So you're going to have to find the molar mass of the urea, but it actually turns out that that's given to you, so you don't even have to do that. So divide how much you have of the urea, which is 35 grams, by how much 1 mole weighs, which is 60 grams per mole. So divide 35 by 60, that gives you the number of moles of urea. And then to get the number of moles of water, how many grams of water do we have? We have 75. Divide that by 18, and that gives you the number of moles of water, and then you add the two number of moles together to get the total, and then divide the number of moles of water by the total, and that'll give you the mole fraction of the water. Oops. Excuse me, which you would then multiply by 23.8 torr, which is the vapor pressure of water at that particular temperature. You might want to just try to remember as kind of a rule of thumb in case you need it on a test that at 25 degrees centigrade, the vapor pressure of water is about 25. It's actually closer to 24, but it's just a rough rule to remember. Okay, so anyway, that sets that one up, and I'm going to let you guys do this one on your own. So let's move on. Here are the answers on the next slide, and then let's go to the next slide. Which of the following will have the lowest freezing point? Okay, so remember the formula here is that we are going to get the change in temperature, which in this case we want the highest change in temperature because when we subtract it from 0, we get the lowest freezing point. So which one of these things is going to give us the highest value for delta T? So remember the formula is IMK, where I is the number of particles, M is the molality, and K is the constant. But the constant is going to be constant for all of these. So let's just get rid of it because it'll be the same for all of these. So just mark it out. So we need the I and the M. So in other words, for each one of these, 5 choices, we want the I and the M. And we're going to get rid of water right away because it's going to have the highest freezing point of 0. All of the other ones are going to be something that's below 0. So just move A out. It's off the table. All right, for this one, we want the I times the molality. I is 1 for sucrose. Let's just do all the I's. So for FeI3, it's 4. For glucose, it's 1, and for KF, it's 2. Okay, so here we're going to multiply 2 times 0.5. Here we're going to multiply 1 times 0.6. So 2 times 0.5 is 1. That's the highest one yet. 4 times 0.24 is going to be 0.96, so that's less than 1. And 1 times 0.6 is 0.6, which is less than 1. So the answer is going to be E here. Next slide. Okay, so you can look at this on your own. I actually did it all out down here. Let's go on to the next one. This one is one of the hard ones, which actually it turns out I can set it up kind of quickly, and then we'll go look at the answer. But this is a molar mass question, like one of the ones that we looked at in the lecture notes. So to do molar masses, as I said, you have to find a certain volume or mass, and then you have to find how many grams of your stuff you're interested in is in that mass or volume, and how many moles are in it, and then divide them grams per mole, and that'll give you the grams per mole of the molar mass. All right, so our formula here, which I'm just going to say this verbally because it takes too long to write it out. Delta T is IMK, but for a liquid, we usually assume I is 1, so just leave that out. So delta T is going to be MK, and we know what the delta T is, and we know what the K is. So the K is here, and the delta T is here. We'll change it to plus, because we're going to we remembered that whenever we do the freezing point depression, we just remember to subtract it. So delta T is going to be 3.33 degrees centigrade. K is going to be 1.86. So delta T divided by K is going to give us M, which means 3.33 degrees centigrade divided by 1.86 degrees centigrade slash M will give us the molality. So the first thing we'll want to do is do that. And what that's telling us is how many moles of this unknown liquid we have in 1,000 grams of the solvent, which is water in this case. And then we realize we don't have 1,000 grams of water, we only have 90. So we multiply that value by 0.09, or you can set it up as a ratio and proportion, or you can look at it like convert that to 0.09 kilograms. However you want to do it, that's going to give us how many moles we have in this amount, in this 90 grams of water. We're going to have a certain number of moles. And we also already know how many grams we have because they just gave it to us. So we can just divide the number of grams that there are in this particular volume by how many moles we got when we did the problem. So let's go to the next slide and look at the answer. So the molality turns out to be 3.33 divided by 1.86, which is about 1.8 mole. And so the way that I actually did it here is slightly different from the way that I said. So let's just look at what I wrote here. Well, no, it's the same. So 1.79 mole means moles of solute per kilogram of solvent, but we've only got 90 grams here of the solvent, which is water. So that converts to 0.09 kilograms. And if we multiply that out, this amount, we have 0.1611 moles. In other words, in 90 grams of water, we have that many moles that I just underlined. And we also have 10 grams as we saw in the problem statement. So if we just divide the 10 grams by the 0.1611 moles, we get the grams per mole, which is 62.1 grams per mole, and that is the molar mass. Now it turns out that, I mean, these are probably the hardest problems in the chapter. So you'll really, even though it didn't look that hard when I just did it, that's because I've done this so many times, but you'll probably want to take a little bit of time and maybe pause this and look at this 2 or 3 times to make sure that you understand what's happening here. Okay, next slide. And this is another one. We're going to do the same thing here, but instead of using that formula, we're going to use our other formula for osmotic pressure, and that was pi equals MRT, where M is molarity. R, remember, was 082 liter atmospheres per mole K. And then the T is the absolute temperature, which is going to be 298 here. So we're going to do it the same way, though. We're going to figure out a certain volume, and you can do it, in this case, I think you can do it 2 different ways. You can use 1,000 milliliters or 1 liter as your volume, and I don't remember which way I actually did it, or you can use your 12 milliliters of solution as your volume. We already know that we've got 0.6 grams of nicotine in 12 milliliters. So if we found how many moles there were in 12 milliliters, then we could just divide grams by moles and get our answer. All right, so we have pi equals MRT. And we're told, let's see, yeah, we're told the pi, we're told T, and what else? We know R, so we can figure out M, capital M, which is the molarity, by dividing the osmotic pressure by the temperature times R. And let me re-say that because that could be confusing. Divide the pressure by the temperature, and then divide what you get from that by R. So in other words, divide 7.55 by 298 times 0.082, and then that will give you your molarity, but that's going to be moles of solute, and in this case the solute is going to be the nicotine up here, per liter of solution. And then at that point, you can leave that one alone, and then you can say, okay, if I've got 0.6 grams of nicotine in 12 milliliters, how many grams of nicotine would I have if I had 1,000 instead of 12? Which means you'd have to set up a ratio and proportion, where you'd write 0.6 is to 12 as X is to 1,000. You see what I'm saying? Cross multiply, solve for X. Or you can leave it the way it is and say we've got 12 milliliters of solution and we've got 0.6 grams of nicotine. So once I find my molarity, I'm going to know how many moles I would have in 1,000 milliliters. So I can just multiply that by 0.012 to get it to how many moles I'd have in 12 milliliters of solution. And that is also just a shortcut of doing a ratio and proportion. So let's go to the next slide. So first of all, I rearranged the original equation here, and we're assuming that I is 1 because nicotine is a covalent compound. Rearrange it to get M by itself and do what I said earlier, and we get that the M is 0.309 moles per liter. Now what I'm saying is you can either leave it that way and find out how many grams you would have of nicotine if you had, instead of 12 milliliters, you had 1,000. Which I don't think that is the way I did this. Or you can do it the other way, where you say, okay, we know we have 0.6 grams in 12 milliliters, so how many moles would we have in 12 milliliters? And so we just figured out that in 1,000 liters we would have 0.309 moles. So if we multiply that number by 0.012 to represent the 12 milliliters, the liters here are going to cancel here, and we're going to wind up with 0.0037 moles if we only had 12 milliliters of solution. So now we know how many moles we have in that same volume, and we know how many grams we have in that same volume. So just divide grams by moles and you get the molar mass. So divide the 0.6 by 0.0037 and you get 162, which if you round it would be 160. And that matches up with answer choice C. Let's go to the next slide. We're just over an hour. Okay, we still have a few more of these to do that are going to take some time, but I'm going to just do, I think out of this, I think there's either 3 or 4 of them. And so everything from now on is actually verbatim taken from an old final. And I put them in here at the end of this problem set. So this used to be, we would be finished with the problems at this point in the way that I've done them in the past. But I added on about 5 or 6 more problems that were taken verbatim from a final because they put them in the final exam and I didn't think my students were exactly ready for them. So let's just do these real quickly. Here, this one anyway. The next few, though, are going to take longer. So Ki, first of all, Ki is an ionic compound because potassium's from the first column or group. It's an alkali metal. Iodine is all the way in the nonmetal, so it's ionic. So if you put it in water, it's going to break up into K plus and I minus. So what we would expect it to be the most soluble in would be something that's polar at least. And so look at your choices here. That is not polar because carbon and hydrogen, same thing here, have about the same electronegativity, so there's no polarity there. And also, even though chlorine is electronegative more so than carbon, each of those CCl bonds will be polar, but because they're in a tetrahedron, as you hopefully remember from 1311, they cancel each other out, so that's not polar. That's carbon tetrachloride, by the way, which is sometimes called carbon tet. This is polar. The reason is because that O will draw electron density away from the H and the C, and it will become partially negative, which I'm not going to try to write that. I'll just write negative. And then the H and the C will be positive. So it's polar. So this is going to be more soluble in something that's polar because it can associate itself with those partial charges and solvate. The partial negatives and positives will solvate the plus and the minus charges better than any of the other stuff that we talked about. Okay, so let's move on. The answer is going to be B. Let's move on. And I'll let you stop here if you want and read the answers in the explanation. But I'm going to move on to another one, which is harder. So here are some that were on one of the final exams, and it was like the first 3 questions were all almost exactly the same. And I don't think my students even understood how to do it. So that's why I've been including these ever since. Because we don't exactly talk exactly how to do this particular type of problem. Now, you could figure it out if you knew what we did learn, but it's just that I'd rather that you see it ahead of time. So let's just do this together. So the trick here, and I'm going to put an asterisk, is to assume that you have 1,000 liters, milliliters, sorry, 1,000 milliliters, or 1 liter. So you put everything in the situation as if you had 1,000 milliliters. So assume that you have 1 liter. I'm going to write 1 liter because it doesn't take as long. Assume 1 liter. Whoops. 1 liter. And that's the really key to the whole problem. So let's do that. So we have 15% by mass solution of lactose, and they give us the molar mass. In water has a density of 1.062 grams per milliliter at this temperature. The temperature turns out not to matter. What is the molarity? And so I think there are 3 of these problems in here. And I mean, I could spend 10 minutes on each one of them, but I don't want to do that. So what I'm going to do, I think 2 of these problems are molarities. So I'm going to do one of those and then let you guys do the other one. And then I think one of them, I'm sure one of the other ones is molality. So I will go through that one. But what we're going to do here is we're going to assume that we have 1,000 milliliters. If we assume that we have 1,000 milliliters, and if 1 milliliter has a mass of 1.0602 grams, then 1,000 milliliters would have a mass of 1,060.2 grams. And that's, I mean, believe it or not, that's like the key to the whole problem. Because once you know that, then you can multiply 1,060.2 grams times 0.15, which is the mass percentage of lactose, and get the number of grams of lactose you would have if you had 1,000 milliliters, which is exactly what we want for molarity. So once we know how much mass we have of lactose, how many grams we have, we can take the number of grams that we have and divide them by how much 1 mole of lactose weighs, which is 342.3, and that'll give us the number of moles of lactose, which is the solute in this particular case. And that's going to give us the top part of our fraction. And then to get the denominator, all we need to know is how many milliliters we have. But we know that already because we assumed 1,000 milliliters or 1 liter. So the bottom part of the fraction would just be 1 liter, so we're basically finished. at that point. We just have to convert it to moles and then divide by 1, which is going to not change the answer. So let's go to the next slide. So you'll notice here we start off by assuming that we have 1 liter, and that is the key to this whole problem. So if you can just remember that when you get this kind of a problem, just remember we want to assume that we have 1 liter, then everything else kind of falls into place. So if the density is 1.0602 grams in 1 milliliter, if you have 1,000 milliliters, it would be, let me come back over here, it would be 1060.2 grams if you had 1,000 milliliters. And now you know that out of that 1060.2 grams, 15% of it is going to be for the lactose. So multiply 0.15, which is what you get when you convert 15% to a decimal. Just move it back over 2 places to the left and get rid of the percent sign. And then multiply that by the 1060 and you get 159 grams of lactose, which you can then divide by 342, which was the molar mass of lactose given here. And it gives you the number of moles of lactose, and that's already in 1 liter of water, so you're finished. Because the answer is going to be that if you have 0.4646 moles of lactose in 1 liter of water, then by definition, the molarity is 0.4646. Okay, so I mean, these can be really difficult if you don't know what you're doing when you start. So hopefully this will help. Next slide. And then here's another one that's asking us to do the same thing. It's exactly the same process. So we're trying to find the molarity here. They're giving us the density. So assume you have 1,000 milliliters. Move the decimal place over here 3 places to the right. You'll have 1,100 grams in 1 milliliter. Multiply that by 0.1 for the 10%. That will give you the mass of the cadmium sulfate, which you'll then divide by 208. That gives you the number of moles of it in 1 liter, and also your answer. So let's go to the next slide. So when we divide 110 grams, which is what we get when we multiply 0.1 times the 1,100, divided by 208, which was given here, that gives us the number of moles. And it turns out that that number of moles happens to already be in 1 liter of solution. So we're finished. We can just write our answer out. 0.528, which matches answer choice A. Next slide. For this one, we have a different situation where we're trying to find the molality. And so for this particular problem, we're going to do it the same way we did the previous two, except we're going to make a slight change because we don't want 1 liter of solution. We want 1,000 grams of solvent. Start off the same way by assuming you have 1,000 milliliters. So move this over 3 places to the right. So you're going to wind up with 1,117 grams if you had 1 liter of this stuff. And then again, multiply by 0.2 to get the mass of the ammonium sulfate, and then divide by its molar mass to get the number of moles of ammonium sulfate. In this case, however, you're going to then multiply this number right here again, and this is something we did not do in the previous two problems. So we multiply it by 0.8 to see how many grams of that 1,117 was for the whatever it's being dissolved in, which it looks like it must be water. So anyway, I guess it really wouldn't make any difference. So so do it the same way we did the last two for the first part. And then for the second part, we need to divide it by how many kilograms we have of the solvent, which we don't even know what it is, so assume it's water. But again, it doesn't matter actually, because if we multiply 0.8 times 1,117, that's going to give us the number of grams that we have. And so we can just divide the number of moles by that number converted to kilograms. So for example, I mean, just looking at it, gosh, it's going to be, let's see, 800, 80% would be 800, but it's more than that. Let's just say it's 850, and we'll look at the right answer in a minute. Let's just say that out of that 1,117 grams total, that 850 grams were the solvent. In other words, when we multiply that number right there, 1,117, where we've, not this number, but this number, if we convert it to 1,000 of these, would be 1,117. If we multiply that by 0.8, and I'm getting the 0.8 because if the solute is 0.2 and there's only two things in here, then the solvent has to be 0.8. That's where the 0.8 is coming from. So I'm saying if I multiply that number by 0.8, I'm going to get, I mean, that's probably not right. What is that going to be? 0.8 of 100 is 880. So it might be something more like 890 grams. Anyway, whatever it is, then you convert that to kilograms. So we'll see the actual answer in just a moment. So that's supposed to say it's supposed to say 890. So if you convert that to kilograms, it would become 0.89 kilograms. I guess I could pause this thing while I do all this writing, and that would make it where it wouldn't waste all this time. Okay, so whenever you figure out the number of moles that you have of the ammonium sulfate, then you just divide that by the number of kilograms, and that will give you the molality. And we've seen that in previous problems. Next slide. Okay, so assume you have 1 liter of solution, so you would have 1,117 grams of that, and when you multiply that number by 0.2, it gives you the number of grams you have of the solute. But when you multiply it by 0.8, it gives you the number of grams of the solvent, which did turn out to be about 890 grams. So here, we're going to convert this 893.6 grams to kilograms by moving the decimal place right there to 0.893 kilograms, which of course, I did it a different way on this one, or here it's at the bottom. So 0.893 kilograms is what we'll divide by. And when we multiply 0.2 times 1117 total, we get 223 grams of the solute, which we divide by its molar mass, which doesn't look like they gave it to us. So you would have to do this one yourself, it looks like. So sulfur is 32 plus 4 times 16 plus 2 times 14 plus 8 times 1. Let's see what that turned out to be. 132 grams per mole. Yeah. And then when you divide how much you have by how much 1 mole weighs, you get 1.69 moles, which is in 0.8936 kilograms. So divide 1.69 moles by 0.8936 kilograms down here, and that will give you your answer. Or you can do it the way I did it here, which is going to give you the same answer. All right, so those are maybe the hardest ones in the whole chapter, or maybe, I don't know, the ones that we did where we had to find the molar masses were also kind of difficult. So those are the ones I would really concentrate on. And then don't neglect the other ones, but it's just that these are going to probably take more time. All right, so let's go to the next slide. And then let's see, I think this is either the last one or the next to the last one. Dissolving a solute such as KOH, which is going to break up into K plus and OH minus, because as you'll want to start trying to remember now, KOH is a strong base. So it turns out there are 7 strong acids, which we'll need to memorize, and 7 strong bases, which we'll need to memorize. So strong acids break up completely in water, strong bases break up completely in water, and then also what we call soluble salts will also break up completely in water. We just assume that they completely break up, even though, as we know from the lecture notes, that they don't really completely break up, but we're not going to worry about that fact. So KOH turns out to be one of the strong bases. Sodium hydroxide is another, potassium hydroxide, and then there are 5 others, which we'll get to. Anyway, when it is put into water, it will break up into K plus and OH minus, is what I'm trying to say. Anyway, when you put anything like that into water, what happens to the vapor pressure? Well, the water can't evaporate as readily anymore. Like if these little dots that I'm drawing are the waters, then if you put some kind of a solute in there, like let's make X's here, the X's not only kind of block access to the waters to get out, but they also attract the waters, especially something like KOH, where you have a completely positive charge on the potassium and a completely negative charge on the OH minus. So the waters are polar and they have partial negatives. So the partial negatives would be attracted to the K pluses and the partial positives would be attracted to the OH minuses. And anyway, all of this combined means that it's going to tend to hold the water more so down into solution. So occasionally one of them will find its way up to the surface and then escape out into the atmosphere. but not as many as before. So we call that a lowering of the vapor pressure, and I'm going to have to try to wrap this up. But so when that happens, what happens is that, first of all, the melting point goes down, the boiling point goes up, and the osmotic pressure goes up. Anyway, these don't deal with the osmotic pressure. They deal only with the boiling point, the vapor pressure, and the melting point. And so this C here is actually what I just said. If you dissolve something in a solvent, it will cause the vapor pressure to go down. And the reason is for why I just said over here, for that reason. So it will go down. So that must mean the other answer choices must be wrong, or are wrong. So we said the melting point should go down. So this A is wrong because this is an increase in the melting point. And then it's the only one that deals with the melting point. For the boiling point should go up, and this says it goes down, so that's wrong. And also no change is wrong because it'll go up. And E says no change in the boiling point of the vapor pressure, which frankly, I don't think I've ever read that choice before, because I've always just seen that it was C, and then I've just gone on to the next problem. But I mean, now that I look at E, it doesn't even make sense. So I'm just going to eradicate it. Okay, so the answer is going to be C. Let's go to the answer. So the answer is C. Let's go to the next slide. Okay, so we're done. Well, actually, that didn't take as long as I thought it would. In fact, it took a lot less than I thought it would. So anyway, that's it for chapter 13. All right, so just as a reminder, you'll want to review back over these periodically, because we will be using things like molarity and molality, but throughout the course, but we won't be using like Henry's law, so you'll want to keep reviewing it. So that wraps up chapter 13. So we'll move on now to chapter 14, which is kinetics, which deals with zero, first and second order reactions. And then we'll move on to the main topic of the whole course, which is chapter 15, which is equilibrium, where we set up equilibria. So chapter 14 is going to deal with rates of reactions, and chapter 15 is going to deal with reactions that go in both directions, which are called equilibria. So let's go ahead and stop now, and I'll see you in chapter 14.